Hey there, brain explorers. Welcome to another deep dive. And let me tell you, today's topic is a big one. We're talking about those behind-the-scenes messengers that quite literally make our brains tick neurotransmitters.
Yeah, it's all about whispers, not shouts when it comes to brain communication. Every single message, every tiny molecule is critical for pretty much everything we do. How we think, how we feel, even how we move and learn.
Okay, so chemical messengers, I think most people listening have probably heard the term neurotransmitter before, but have you ever stopped to think about how scientists know when they found one? I mean, it's not like these molecules put out a welcome mat.
It's surprisingly complicated. It's kind of like, imagine trying to overhear a single conversation in a really loud and crowded market. That's kind of what those early neuroscientists were dealing with. But eventually they figured it out, came up with a set of criteria, kind of like I don't know, like a molecular fingerprint analysis to identify these elusive messengers.
Okay, I like that. A molecular fingerprint.
So what are we talking about here? What are the ground rules for a molecule to earn that neurotransmitter badge?
Well, first and foremost, it's got to be local, synthesized and stored within the neuron itself, not just passing through from other parts of the body.
So not just a forwarded message, it's got to originate from the sender. Makes sense.
Yeah.
What else?
Timing. Timing is everything. The molecule can't just be firing off randomly. It has to be released on cue, precisely when that neuron is activated. Like a perfectly timed text message. Okay, no reply, all mishaps in the system, I got it. But how do we know the message is actually getting across? It's not like we can just ask the receiving neuron if it got the memo, right?
Right, and that's where things get really clever. Scientists have to become master mimickers. They have to figure out how to apply that same molecule artificially and then see if they get the same response from that receiving neuron as if, the real deal had been sent.
Wow, talk about a high bar. Honestly, it sounds like finding a needle in a haystack of neurons.
Oh, it definitely is. But it is possible, and that's what makes this deep dive so interesting.
Well, our sources definitely highlight a few of these game-changing techniques: immunohistochemistry, in situ hybridization, and one that honestly sounds like it's straight out of Star Trek, microentophoresis. I mean, what?
Yeah, it's wild. Each one is like getting a different lens to view this microscopic world, really revealing these processes in completely new ways.
A cellular treasure map. I'm intrigued. Walk me through it.
So picture this. Scientists can actually tag antibodies with fluorescent colors, right? And these antibodies, they act like little bloodhounds, sniffing out and binding to the neurotransmitter molecules. So then when you look at these brain slices under a microscope, it's like a city skyline lighting up, revealing exactly where those molecules are.
Okay, that is incredibly visual. Now, what about in situ hybridization? Is that working on a similar principle?
It's a little bit different. So instead of the skyline, we're talking blueprints, right? So imagine, instead of seeing the molecule itself, you're seeing its mRNA, the genetic instructions for building that molecule.
So it's like the difference between finding a delivered pizza and finding the recipe card. Both tell you pizza's involved, but in different ways, right? Okay, you've piqued my curiosity. What about that Star Trek technique, that microentophoresis?
All right, so think of like a microscopic pipette, carefully placing a tiny droplet of a substance directly onto a single neuron.
So each technique, it's like it provides a different clue, a different piece of the puzzle. And it's by putting all those pieces together that scientists are able to confidently say, yes, this is a neurotransmitter, and actually track its movements within the brain.
Exactly. But understanding what these messengers are is only half the battle. The really fascinating part is figuring out how they actually exert their effects, and that's where this idea of receptor subtypes comes in.
Okay, now we're getting somewhere. We're about to enter a world where one neurotransmitter can sometimes feel like a whole team of messengers, each with its own agenda. Welcome back, neuronavigators. Last time, we were talking about how scientists identify those stealthy chemical messengers, the neurotransmitters, but now we're going to actually follow those messengers to their destination and see what happens when they arrive.
And it's not as straightforward as you might think.
Yeah, our sources have definitely hinted at that.
It's more than just sending a simple text message from A to B. Think of it this way. Imagine if that text message could be read on 5 different devices, and each device triggers a completely different action based on that one message.
Okay, so it's like having those separate inboxes, right? Like you've got your work emails, your online shopping, maybe even a secret account for cat videos.
Exactly. And just like your inbox is going to determine what happens to that email, these receptor subtypes determine how a neuron responds to a neurotransmitter.
So one neurotransmitter can have multiple different, personalities almost.
In a way, yeah. It's all about which receptor subtype it binds to.
So how in the world do scientists begin to unravel this? It's like a tangled web of receptor subtypes at this point.
It takes a lot of careful research. They often use drugs agonists that mimic the neurotransmitter and antagonists that block it to see how different receptors react.
So it's about finding the right fit, like a key in a lock. Speaking of fitting, our notes mentioned acetylcholine, or AK, and it's a role in muscle tissue, right?
Yes, acetylcholine is a great example. It has these two main receptor subtypes, nicotinic and muscarinic. And they really highlight how different the effects of one neurotransmitter can be.
Okay, break it down for me. What makes these subtypes so different?
Well, take nicotine, for example, found in tobacco. It acts as an agonist at nicotinic receptors, which are highly concentrated in skeletal muscles.
Which is why, like, nicotine can cause muscle twitches and even paralysis in high doses.
Right, but then you have muscarine, which targets muscarinic ACE receptors, and those are found in places like the heart. And muscarine, unlike nicotine, can cause a dangerous drop in heart rate. So same messenger, very different outcomes.
That is a powerful example, and it seems like these receptor subtypes, they're almost like a secret code, a way for the brain to fine-tune its messages.
It's true, this diversity is actually key to the brain's complexity.
But with complexity, of course, comes the potential for things to go wrong.
Oh.
And that brings us to two of the most abundant neurotransmitters in the brain, glutamate and GABA, the dynamic duo excitation and inhibition.
Right.
So if the brain were like this bustling city, would it be safe to say that glutamate is kind of like the power grid?
I'd say that's a pretty accurate analogy. Glutamate is the primary excitatory neurotransmitter, and it's essential for tons of processes like learning, memory, sensory perception. But too much glutamate, kind of like an overloaded electrical grid, it can actually be toxic to neurons.
Oh, wow. So too much of a good thing can be bad. You're saying the same substance that's essential for brain function can also be harmful.
Yeah, it's all about balance. And this toxicity, we call it excitotoxicity, it's linked to overactivation of these NMDA receptors, a specific type of glutamate receptor.
So too much glutamate essentially overloads the system.
Yeah, and it's like a dam breaking. You get this excessive influx of calcium ions rushing into the neuron.
And too much calcium inside a neuron, that's bad news, right?
It can be. It triggers this cascade of events that can damage and sometimes even kill the neuron.
And this isn't just a theoretical concern either, right? I mean, glutamate excitotoxicity, this plays a role in certain neurological conditions.
Absolutely. It's a significant factor in things like stroke and traumatic brain injury.
So then GABA, it's like the brain's chill pill, right? It counteracts those excitatory effects of glutamate.
Exactly.
And it's interesting because, we know that these calming effects of GABA can be manipulated. And this is where things like benzodiazepines and alcohol come in.
Right, because they essentially enhance the effects of GABA.
So they kind of turn up the volume on that calming message.
Yeah, you could put it that way.
But of course, there's always a flip side. And with something like this, it's usually, the risk of dependence.
Absolutely. That's why it's so important to maintain that balance.
Right. Because it's like you need a stronger and stronger dose of chill just to feel normal.
Exactly.
Which is a good takeaway from this. I mean,
Yeah.
understanding these neurotransmitters and their effects, it's not just about textbook knowledge. It's about understanding how even subtle shifts in our brain chemistry can have these huge implications for, well, everything.
It's true. These systems are incredibly complex.
Okay, so we've been talking about neurotransmitters traveling on this one-way street, right? From the presynaptic neuron to the postsynaptic neuron. But what if I told you the brain has a few more surprises up its sleeve?
Oh, there are always more surprises when it comes to the brain.
Welcome back, brain explorers. We've journeyed into the world of neurons, decoded those chemical messages, even met those receptor gatekeepers. But get this. Just when we thought we had it all figured out, turns out the brain has a few more tricks up its sleeve, right?
Always. The brain loves to keep us on our toes.
That's for sure. So last time we were talking about this idea of neurotransmitters traveling on a one-way street.
Right from presynaptic to postsynaptic neuron, the classic model.
Exactly. But we're hearing whispers of a different kind of pathway, something that challenges that whole idea, something about retrograde messengers.
You got it. We're talking about signals that actually travel backwards across the synapse.
Hold on, backwards. You're saying the receiving end of the synapse can actually send messages back to the sender. That's like what my phone gets a text, and instead of hitting reply, it somehow sends a message back through the original sender's phone.
It's a pretty wild concept, right?
Yeah.
Like the postsynaptic neuron is no longer just a passive recipient. It's like, hold on, I need to interject something here.
Okay, so what's the point of this two-way communication? What's the purpose?
Well, think of it like a feedback mechanism,
Yeah.
a way for the brain to fine-tune its own activity. So let's say, for example, the postsynaptic neuron is getting bombarded with signals, like
Yeah.
it's totally overwhelmed. It can actually release these retrograde messengers to tell the presynaptic neuron to, ease up on the gas a bit.
So it's like a way for the receiving neuron to regulate its own input to keep things from going haywire.
Exactly. It all comes back to that balance we keep talking about. And there's a pretty fascinating class of retrograde messengers that you might be familiar with, endocannabinoids.
Wait a minute, endocannabinoids, as in related to
The
cannabis.
very same. Our brains actually produce their own versions of these molecules, and they play a key role in regulating neuronal activity, particularly by tapping into this retrograde messaging system.
Okay, now you've got my attention. How do they work? Give me the full download.
All right, so picture this. The postsynaptic neuron is firing rapidly,
Yeah.
tons of activity, which means calcium ions are flowing into the cell.
And this is where it gets interesting because these endocannabinoids, they're lipid soluble, right? So they can slip through cell membranes almost like, I don't know, like undercover agents.
Exactly. They sneak out of that postsynaptic neuron, they cross the synapse, and guess what? They bind to receptors on the presynaptic neuron.
Okay, so they're like sending a secret message back to home base.
You could say that. And the primary target, the CB1 receptor.
Hold on, CB1, as in the same receptor that THC binds to?
You got it. The very same. Which just goes to show you how much we're still learning about this stuff.
So we're talking about a naturally occurring system in our brains that's influenced by the same molecule found in cannabis. That's wild.
It is. It's like our brains have this built-in chill switch.
So what happens when these endocannabinoids bind to the CB1 receptors on that presynaptic neuron? Do they shut the whole operation down?
Not exactly a complete shutdown,
Right.
but they dampen the activity. See, one of the main effects of CB1 receptor activation is actually to reduce the influx of calcium into that presynaptic neuron.
And less calcium means less neurotransmitter release, right? Like turning down the volume on neuronal communication.
Exactly. And it just goes to show you how dynamic this communication really is. It's not a one-way street at all.
It's definitely been an incredible journey into this intricate world of neurotransmitters, wouldn't you say? From those molecular fingerprints to these, like, mind-bending retrograde messengers. It's amazing how much is happening in our brains at every single moment.
It really is. And the most exciting part is we're still just scratching the surface. There's so much more to discover.